Okay, so the characteristic polynomial, okay, where's my characteristic polynomial here? So which is the determinant of this matrix. So once again, probably this with the circles over there. It's probably the best way to remember what it's all about. And actually for the final is the determinant of this matrix is what gives you the eigenvalues, practically speaking. So for the chance, generally speaking, it's 2 by 2 matrices are really so limited in scope and the applicability, and so you would have to deal with n-dimensional situation, and therefore with the n-dimensional matrix, and therefore with an n-dimensional determinant. Okay, but practically, if you were to demonstrate that you know how to deal with eigenvalues, that's what you do. You form this matrix, form the original matrix A, B, C, D, which is your linear operator. You form this matrix minus lambda. Okay, see where it appears. That lambda is your unknown. And once you solve for it, fortunately, because of 2 by 2, the end result is a quadratic polynomial. And then you'll have your quadratic equation, which will produce the eigenvalues. Okay, so which is already without eigenvectors, it already tells you a lot about this linear operator. We can classify them. So once again, this is the abbreviated way of writing what I have here. Okay, so so once again, the determinant of this kind of weirdly defined matrix. A is the original, and then we create this A minus lambda I. Well, the same matrix 2 by 2. You take this determinant, which gives you a characteristic equation, which will produce the eigenvalues. Okay, so that's the good news. The bad news that we might end up with a quadratic equation which has no solutions. Okay, so in other words, the one with the determinant negative. Okay, determinant is negative. There are no solutions, and therefore we cannot proceed. There is no, well, it means the good news is that it's not uninformative. It tells that there are no real eigenvalues. There are no real eigenvectors, which means that there isn't every vector is rotated. Okay, so every vector is rotated by some degree, and therefore, so that's informative. Okay, even without eigenvectors, which don't exist. To sort it out completely, we would have to unfortunately go into entirely subject that takes another semester to fully learn its complex numbers. And a complex linear operator and everything starts over pretty much. So we'll just take the what's on the surface, like I said. So if there are no there is no way around that part. So if there are no lambdas in the as solutions to this equation, then there are no eigenvalues. Okay, so which means that it is rotation. Okay, so once again, that's how it's happened. The quadratic polynomial might have 2, 1, or none x-intercepts, and that's exactly what we're talking about here. So I'll skip this, and this is the classification. So even with or without knowledge of complex numbers, we can classify the linear operator based on its eigenvalues. So eigenvalues are distinct. So once again, that case number 1, 2 distinct eigenvalues. Okay, so what does that tell us? The term is positive, eigenvalues are distinct. Okay, operator A non-uniformly rescales the plane in the distinct directions of the corresponding eigenvectors that we haven't found yet. Okay, so once again, we have a multiplication, something like this, and then we stretch along one axis and we stretch differently along another. Okay, so that's the typical situation. Case number 1. Case number 2, determinant the discriminant. Discriminant is 0, which means that we have a touching of the graph. The graph touches the x-axis, and there's only one solution. In which case the eigenvalues are equal, literally. So eigenvalues is in a way 2 eigenvalues. It's not 2 anymore. Okay, so it's the same eigenvalue. Even though it's a kind of a degenerate transitional case. Okay, so as you can see, it is a transition. The transition to case 3 is this. Okay, so this is the transition. So this is generic, and this is the transitional edge case when we are going from one to another. So if you're moving your parabola up, okay, so at some point it has 2 intersections, at some point has none, and in the middle, for an instant y, I say it's transitional. For an instant, there is only exactly one intersection. So it's a typically, if you take a parabola and throw it on the plane, it's either typically will have either two intersections or none. You have to throw very specially in, so it would land in such a particular way that it will have exactly one point in common with the x-axis. So nonetheless, it's the case, and as you can see, that is a special case of when you have uniform rescaling of the plane. Okay, so that's a very simple case. It is simply pretty much multiplication by a number. And then there are no eigenvalues. Discriminant is equal to 0, so there is a rotation. When I'm not saying it is a rotation. Okay, so it's not a rotation necessarily, but maybe a rotation plus something. Okay, so it is a rotation, and combined with maybe stretches once again. So stretches do not go away. So we just, but once everything, the plane is rotated, it's not even rotating the plane. I don't know what a good language to use. Rotates all or each vector. That's what it does. So each vector is rotated, but also maybe rescaled in addition to that. So that's the information that we've got. Okay, so like I said, not finding, using only the characteristic polynomial and not finding the eigenvectors gives us nonetheless a pretty good classification of the linear operator. Okay, so then nonetheless, so with that in mind, we do not stop here. We need to find what is the significance of the eigenvectors. You can tell, right? So this is the direction along which, as we know from the beginning, that in these directions there is stretch. Period. Okay. So, but it is especially important when you go to high dimensions. So let's examine this. The significance of the eigenvectors as opposed to just eigenvalues. Eigenvalues give us this nice classification, and that's good, but no, there is more to it. Okay, so once again, that's the definition of the eigenvector. Okay, so we presume that we have found the eigenvalue already, so that part is given. So once again, examples, quickly going through some of the familiar examples. This is two stretches in the along the axis by 2 and by 4. So there is, and you can see what happens clearly. My circles become ellipses, and it is stretched more in the vertical direction than the horizontal direction. Okay, so that's fairly straightforward. In between, we have this fanning idea. Yeah, you can try to imagine what happens in high dimensions. So for example, in dimension 3, what's going to happen? So then there will be well, okay, so let's take a minute and ask ourselves. We should probably keep asking that question every time we do a two-dimensional example. What happens in dimension 3? So in dimension 3, the matrix is 3 by 3. Therefore, what does it tell us about the characteristic polynomial? Well, I mean, yeah, actually, the unfair question. We did not discuss the determinant of a 3 by 3 matrix, but I only mentioned that once, and so the polynomial will be cubic. Okay, so that's the unfortunate thing. So the complexity does increase with increase of the dimension, and so that polynomial becomes high and high degree. So cubic polynomial already. So we have a quadratic formula. We do not have a cubic. Well, we do have it, but right now nobody remembers. It's a fairly long formula if you haven't seen it. There's a quartic formula too, and it's also very complicated. Even more complicated. It'll take like a half a page. And then there is no formula for 5th degree. There is no formula in 6th degree. There is no formula. There is literally no formula because it does not exist. And so the algebraically things become intractable. And so we just enjoy the two-dimensional case. But let's not assume that it is going to work out every time. So that's why actually understanding what eigenvalues and why we care, why they is so important. Let me remind you, maybe you can relate to certain things in like data analysis. So your data in two-dimensional case might look like this. Okay. Which is, so it has a center and it has, but otherwise uniformly distributed. Or you can have something like this. Okay, so in other words, it's stretched out. Okay, so to detect in which direction that is stretched out is basically on doing that's over here is an eigenvector, roughly speaking. Okay, so you can form a certain linear operator to that captures the shape of the data, your data on the right, and then one of the direction, and that you can guess if you look at the data on the right, you can guess that there's a pattern there. They seems to be stretched out along certain line, and there is some deviation to the left or the right, and so there will be stretching along the one axis and shrinking along another axis. Okay, so detecting them will tell a pattern in your data. Okay, so that's a clear pattern, and you discover it is from your knowledge of the eigenvectors, eigenvalues. Okay, so that's the point. Naturally, in dimension n, you don't see any pictures, and so that's why algebra it becomes inescapable. Okay, so that's the point out, and we just let's once again examine some of the examples of two-dimensional cases. So so what happens is very clear. What's happening along the axes, the green stretch, the red stretch. What's in between? We see a fanning. Nonetheless, we could, based on our information about the basis vectors, E1, E2, once again, is one multiplied by 2, the other one multiplied by 4. Okay, so we can detect, just as an example, what happens to the rest of the vectors. So, for example, here's something that we already know, but nonetheless, it's very important to see how how the linear operators affect the vector xy. So, let me just carry out what's the meaning of x and y. Where do x and y emerge? And they emerge as coefficients of the two vectors, where the E1, E2 go. So E1 goes to, which is 0, 1, 0. Okay, E1 is 1, 0. Okay, and where does it go? It goes to 0, 2. So 1, 0 goes to 0. 1, 0 goes to 2, 0. Okay. 1, 0 goes to 2, 0. Okay, that's a stretch by 2. Okay. Secondly, the second vector goes, which is 0, 1, and 0, 1 goes to 0, 4, stretch by 4. Okay, so that's where the matrix comes from in the first place. But now, so that's our knowledge. But now, what about the rest of the vectors? Then the vectors have components x, y, and then you can see over here where those x, y appear. They appear as the coefficients of those two vectors. So the most important things vectors are 2, 0, and 0, 4. These are two vectors, and then this is where they are present now. So that's one. This is the other, and here where they're present. Okay, so those two vectors are actually, we create a linear combination of those two vectors with the coefficient x and y to produce the outcome of any other vector, not just the basis vectors, which happens to be here, happen to be eigenvectors, but also the rest of them. Okay, so any vector x, y turns out to be just a linear combination of those two. So once again, 0, 0, 2, 0, and 0, 4 are those two vectors that can be now used as linear combinations to produce the rest. Okay. So the idea here is actually use the eigenvectors as an alternative basis. So there is no alternative here. It just happens to be the special case of a diagonal matrix when the eigenvectors are the basis vectors. Okay, so the stretch is along the axis. But if, generally speaking, we have a situation when we do have eigenvectors pointing in any direction, once again we can use them as an alternative basis. Okay, and as you can see, it works. Well, let's see how it works out. So this is still the same. So I don't want to do this. So it's still there's an extra flip there. So everything we've seen this before. Projection also we have seen it. So once again, it is a projection. Well, okay. So let's deal with the basis a little bit later. But you can see what happens to the two basis vectors. So one is stretched and the other one is collapsed. So that's what the projection does. So 2x that's the along the first axis, along the second axis, everything becomes 0. And so once again, everything is expressed in terms of the eigenvectors. So 1, 0 multiplied by 2, 0, 1 multiplied by 0, and therefore everything is multiplied respectively by 2 and by 0. So the two components are multiplied accordingly. Okay, so we've seen this example before. This is really what a crucial idea that we did not discuss, even though it did come up a little bit. It is about once again projections, and the kernel of a linear operator is simply all the vectors that go to 0. Okay, so it is in other words it is an eigenspace of 0. That's what it is. Eigenspace of 0. So if 0 is our eigenvalue, which it might not be, in that case we form its eigenspace, and that is the space that goes entirely to 0. So what we have seen here, as you can see, that's the simplest case here. The whole vertical direction collapses, and so so the green is my kernel. So yeah, this is the kernel. Kernel of f. Okay, so naturally, because it goes like this, everything goes into zeros. The zero is in the middle, and everything goes into 0. This one is not in the kernel because that's where it lands. So it lands away from 0. It has a non-zero component, but everything on the green line goes into 0, and so it is an important eigenspace, which happens to be also a subspace. Okay, so generally that's a general picture here. So once again, if we have a projection, then one of the lines happens to be perpendicular to what everything is being collapsed. That line collapses to 0 particularly. Okay, so and that red line is our its eigenspace, and it is a subspace. Okay, so that's what the crucial to understand here is that the kernel is a subspace. Okay. Subspace, remember what the subspace is? Subspace, well, look at the picture. It's a whole line, remember? There are too many subspaces to think about in the two-dimensional case, but every line is a subspace. Subspace means it is a space of vectors that is self-contained. Okay, so this one is self-contained, but this one too. Any line that passes through the origin is made of vectors, but in such a way when you start doing algebra, in what sense self-contained? In the sense that when you start doing algebra within that space, you will never leave. Okay, so once again, these are not there's one vector and you take its multiple. Naturally, if you take the multiple of that vector, say v, and you have another vector, so v plus 2v plus 3v, what is it? It is equal to 5v. So it remains within, it is still a multiple. So if you start with two multiples of v, you have them together, you still have a multiple of v. So that's what it means that it is self-contained, and that's what we call subspace. And then so then we would can speak of the projection on a subspace. We can also speak of a collapse of a subspace, and that what is being collapsed to 0 is called the kernel. Okay, so once again, everything is within that space is within that set to begin with is a vector. But when we start doing algebra within that set, it is as if it is a complete space. Okay, remember the vector spaces we talked about a little, and so that is a way of producing subspaces, especially in high dimensions. In dimension 2, we have only lines. Okay, so in dimension 3, for example, that things instantly become more complicated. So a plane of vectors may be like this. Plane of vectors like this. Okay, so it's not as obvious that if I have two vectors lying within that red plane, I add them together, the end result will be still lying within that plane. Or maybe it is obvious, is it? So once again, I draw two vectors within this red plane. Okay, if I add them together, where does the sum lie? One vector, the other vector. So these two vectors lie within the red plane. When I add them together, the end result will be still within the red plane. Why so? Because you have to remember the construction of the diagram of adding vectors is building a triangle or building a parallelogram. So you never leave the plane. So two vectors determine a plane, okay? And so when you start doing addition, then you're not gonna go like this in the third, even though the third dimension is available, you're never going to go in that direction because that's how addition works. You will stay within the same plane. So the addition of vectors is two-dimensional. So that's the idea of subspaces. In the once again high dimensions, the space itself is high dimension, and the kernels of linear operators might be more also high dimensional. In dimension one, I'm sorry, two. So this is dimension two. There are only two possibilities, and that is the zero, a line that contains through zero, and the whole plane. These are the only three options for the subspace, and therefore for the kernels. But at the very least, it does contain a line. So if you have a vector, then all of its multiples also belong there. That's quite algebraically predictable. So if f of v is equal to 0, then if I take f of lambda v, what happens? Because of the operator is linear, I can just factor lambda out, and I have f of v, which is lambda times 0, which is 0. Okay, so as I have demonstrated that once again, if you have the kernel contains a vector v, then it contains all of its multiples. Why did I put lambda here? So let's call it k. Okay, so once again, a vector v goes to 0 under f. Where does it multiple go? And it also goes to 0. Okay, so that's what the picture here shows. That red black dot in the middle is the origin, and therefore the line passes through the origin, and the vectors are multiples of each other. The vectors within the red line all multiples of each other, and indeed, then so all multiples all will go to 0. Okay, because it is a linear operator. If it was not linear operator, then all bets are off. But everything else is in linear algebra is this simple. Okay, so it is a subspace, and so that it is a special. If you have this case, if your kernel is not 0, if it is 0, then we know what it means. I wonder if you remember what it means. The kernel is equal to 0. What does it tell you? Once again, the kernel is this is the definition. So the kernel is equal to 0 means that the only vector that goes to 0 is 0. Okay. What does it tell you? About that.
The vectors are taken to 0, right?
What?
So that would mean that no vectors are taken to 0, right?
Right. So the 0 always goes to 0. So what we're saying here is that there are no others. So any bigger conclusions that you can make about it. Remind you, so once again, 0 goes to 0 under f, but there is no other vector that goes to 0, so that is not it. Okay, so what does this picture remind you of? This picture. 0 goes to 0, but any other v, which is not equal to 0, does not go to 0. So this picture should remind you of some concept that we have talked about.
So f 1 to 1.
Yeah, that's right. So that is the conclusion indeed. So f is 1 to 1. It is 1 to 1 indeed. So we only assume one thing that there's only one value that goes to 0. So it is 1 to 1 here at 0, but because of the linearity, that conclusion that that is on the surface about 0 also expands to the rest of the vectors. So you cannot have, the conclusion is, you cannot have like v and u going towards the same place, whether or not this vector is equal to 0 or not. So that's what one-to-one means. And all we have to do is just verify the kernel. If the kernel consists of one single value, 0, then we have our whole function is one-to-one, one-to-one on, as a matter of fact, and then well, what's the, remember the condition? We know that our linear operator is one-to-one. There's a number that tells us that story. This determinant, right? Determinant not equal to 0. So when the determinant is not equal to 0, the function is one-to-one, and the kernel equal to 0 is the same thing. Okay, so and that works in all dimensions. There is nothing specific to so that's all right. Nothing specific to the plane. So the certain things, eigenvalues, eigenvectors, as well as the kernel, all of these concepts are n-dimensional. Okay, so we were able to the only thing that we have to reduce ourselves to dimension 2 was actually finding actual eigenvectors and eigenvalues and the determinant. We did not do determinant in n dimensions, which is quite a formula. Okay, so all right, so the projection once again, and this one, this is why it's important. It is a projection. We can fairly easily determine that it's a projection, and by the logic that we just discovered, if we take the determinant of f, it will be 0. Okay, so we conclude then it is not one-to-one, and not one-to-one means projection pretty much in the two-dimensional case. So we know it's a projection, so there's a line somewhere on which everything collapses, and we determine this very easily with nothing but the determinant. But so what is that direction? So if we were to actually determine which way things go, we have to do more. Okay, and so that's why we have to find the eigenvector or eigenvectors for both of them. Okay, so once again, let's go through the computation. The determinant, once again, I form as I have before. Once again, it's fairly straightforward way to form that matrix and then find the determinant, end up with a linear, quadratic polynomial. You don't even have to use the quadratic formula here because, and that's typical because there is no free term here. The one without lambda. Why so? Because we already know we expect as expected because we already know that over here we already know when there's a projection there's a lambda equal to 0. So not both of them, but one of them is equal to 0. That's what remember what that indicates. One of the operators, the projection means that the eigenvalue in this particular direction is 0, and so you expect to have a 0 eigen value, and how does that happen when one of the factors is actually lambda? Okay, so you just factor lambda out, and so you anticipated that, so you know that you're on the right track, and then indeed you rediscover that one of the eigenvalues is 0, the other one happens to be pi. Okay, so let's find the eigenvectors for both. So then we know that for the first one, this is the on what line the f projects. So once again, that picture over here, this one. Okay, so there are two lines, important lines. One on which everything is projected, and the other one is the kernel. Okay, so we start with that green line, and f equal to 5. We have not invented anything new from what we have done before. Fortunately, the eigenvalue is already there. Okay, so then this part that follows. This is fairly easy. Once the eigenvalue is found, it's 5. Then the rest is easy because, well, why so? Because actually the two equations that you end up with are identical. Okay, so look at it. So once again, this is the definition of the eigenvalue, eigenvector rather. So eigenvalue is 5, and then my matrix is 1, 2, 2, 4. Okay, and so the effect of 1, 2, 2, 4 on xy is supposed to be 5xy. So that's the definition of the eigenvector. So v is equal to xy. Okay. And then I break it apart. I break it apart into equations one at a time. I end up with x plus 2y is equal to 5x, and 2x plus 4y is equal to 5y. Okay, now if you look carefully at it, it is yeah. So look at, I bring everything in over here. I bring everything to the left. Okay, so I end up with negative 4x plus 2y. And on the at the top and at the bottom, I have 2x minus y, which is not entirely obvious, but it is actually the same equation. You see it? Right. So if I just multiply the second equation by -2, I will end up with the first. Okay. So and that happens every single time. So same equation. Okay. So and then so I throw one of them out. And over here, I could, for example, express y in terms of x directly because you have only one equation, and that line, it is a line now, right? It is a line, and that's the eigenspace. Okay, that's the eigenspace. That is the line on which everything is projected. Once again, I'm doing, as you can see, I decided not to have a picture here and just do it entirely in an algebraic way, and then discover the conclusions from algebra rather than from a kind of experimentation. So so vector 1, 2, which it goes along this line, y equals, so this is the line, and so so that is the line on which everything is projected. Y equal to x. Oops. Y equal to x. Okay, and then you can guess. So that part is solved, and then and so but along it, let's not forget that along that line is everything is traced by 5. Okay, so that's not line is not intact. Everything is traced by 5. But nonetheless, you can imagine that everything projects on it and then stretched. Okay, so if you prefer to look at it this way. So then you can guess that the line along which the projection is happening is, you want to guess what it is? The line of projection. What is that line? The red line and the green line. So the green line is the one over the stretch by 5, and the red one is a projection. What's the what line is it? It is perpendicular. Okay, good guess. And so perpendicular, good guess indeed. And then so then you can tell what it is. Negative reciprocal, which is y equal -1/2 x. Okay, so you can jump to the conclusion right away. Okay, so so let's do it anyway from scratch. And so the second part is from the kernel. So let's find that's kernel. Okay, so well, where's my algebra? I don't have my algebra here. I'm afraid I have to skip that part. Let me quickly write it out. So I have okay, let me try to fix it. Okay, so the eigenvalue is 0. Okay, so which means that what I end up with is, so eigenvalue is equal to 0. So I end up with x plus 2y is equal to 0. The first line. The second line is 2x plus 4y equals 0. Okay, so once again, we discovered the same thing as before. It's the same equation. And then I can solve for y if I want to, and then I end up with y equal to -1/2 x. Okay. So from the definition of that equation in the middle is the definition of the eigenvector, and then, like I said, there is not as much work as we used to do. when we had to find eigenvector and eigenvalues at the same time. We already have the eigenvalue, so then finding eigenvector, it's not on the one eigenvector, by the way. I don't want to give you that impression. We're finding the whole eigenspace, which is made of a bunch of eigenvectors. They all happen to be multiple of one vector, and you just have to pick which one. It's really, I picked 1, 2 over here, but I could have chosen 2, 4. I could chosen what is -1, -2. All of these we did with candidates. Okay, so they're equally good in that respect. Okay, so anyway, so we discovered that picture. It is confirmed with the computation. Once again, projections along the perpendicular line. The computation that I just did by hand. This is what the spreadsheet does, and making these pictures. Okay, so a subspace of the domain, as I said. Then so this is the once again the typical situation is on the left. And so let's forget about the projections for a moment and look at the non-uniform stretches. The typical situation is on the left, not the typical, but rather the trivial, the simple situation of the stretches along the axes is on the left, and this is the generic. So this is special, and this is generic. But still, the discriminant is still positive. Discriminant is positive, so you have two discriminant of the characteristic polynomial is positive, which means that you have two different eigenvalues, and therefore, according to our classification theorem, there will be stretches, different stretches along two lines, and those two lines have to be found, and they do not have to be x's anymore. Okay, so this is an example of red and green lines are these two axes. So once again, some stretch along the green one and another stretch along the red one. The end result, as you can see, indeed, those circles, after the linear operator has been applied, they become stretched out. Okay, but as you can see, you can see the mismatch, by the way. So it seems that if you look at the picture, I keep pointing it out. The tip of those ellipses do not match the direction of our eigenspace. This is my eigenspace. Look at it. It's my eigenspace, and it is not. It is not matched with the tips, the ends of those ellipses. Okay, so that's just the effect of that we experience. So that's the difficulty that we might have to deal with. So just looking at the data and it's been elongated in a certain direction does not necessarily tell you that in which direction you put a ruler and you can tell what direction of those ellipses is. Not necessarily gives you the eigenspace or eigenvector correct. Okay, so projection once again. So that's what I already did. Okay, so the idea is okay. What is the idea? And the idea is since really the axes are these are the axes. Axes are incidental. Eigenvalues are important. Are crucial. Naturally, we expect to have axes, and they apply to all linear operators. But if we do have a linear operator that we concentrate on, we better concentrate on its eigenvectors than on the axes. Okay, so it may be nothing interesting is happening along the axis, but everything interesting is happening along the eigenvectors. Okay, so then the idea here is that we're trying to follow is let's throw out the axes as in the basis vectors and replace them with the eigenvectors. Okay. And as we know, as I showed you an example, that then it works out. Any two vectors, as long as they're not like this, as long as they're like that, they can serve as an alternative basis. The angle doesn't matter. So 9 degrees is here's the example of 9 degrees. It is incidental. It's not important at all. What matters is that they are as we say, linearly independent. So they're not multiples of each other, and that's how it works out. Okay, so it's one-dimensional. Typically, eigenspaces are one-dimensional, in which case they are made of multiples of these vectors, as I pointed out a minute ago, of the eigenvector, and then that happens to, in case of once again discriminant being positive, you have two different values and two different eigenspaces. And two eigenvectors are not multiples of each other and therefore can serve as an alternative basis. Okay, so typical case. So then if we're using it, that's really what we are after is a new matrix, for my linear operator. So the matrix that linear operators comes from is derived from the standard basis. So once again, F could be once again, so A, B, C, D. And remember where these come from. So this is 0, 1, 1, 0 rather, goes here under F, and 0, 1 goes there. So that's how we know. We take the basis vectors, 1, 0, 0, 1, see where they go, and form a matrix. So that's the standard way. And then, but that's not as the complicated matrix. You have 4 entries, okay? So, and which is okay, maybe 2 or 4. Diagonal matrix has 2, okay, which is not a lot in dimension 2. Imagine that is dimension 3. That is instead of 2 against 4, you have 3 against 9, and then it's 4 against 16. And so if you are able to diagonalize, as we say, your matrix, then it is a much simpler matrix, which we perfectly understand what it does, right? So diagonal matrix, what does it do? It stretches along this vector by lambda 1, along that vector by lambda 2, and so on. So no matter what the dimension is, if your matrix is diagonal, then you have nothing but a bunch of stretches. Okay, so if that's the case, that's what we are after. We want to have a different frame of reference. So which is you may have seen. Where do we see change of frame of reference in real life? Coordinate systems, right? So you might start. Remember, there was a competing who won the zero meridian. You know the zero meridian? Well, I don't know what the answer is. The one goes through Greenwich outside of London, and the other one through Paris. Which one is the right one? For some reason, you can both see them. They're on the ground, made of metal, and but I think the British must have won that competition. But on the other hand, the meters won over pounds. So I'm sorry, over inches. So once again, different frame of reference. Another frame of reference, change of frame of reference is who is the sun in the middle of the universe or the earth? The answer is which one is true, and the answer is whichever you find more convenient. And so that's really what we're after. If you're if you are sitting on the earth and you are studying the sun, it's probably easier to think about that the sun is rotated around the earth rather than vice versa. I don't care what Galileo says. It's just so much easier to think. I'm sitting here, and the sun is just rotating around me. So I am the center of the universe, and that's just much easier to think that this way. So it's a similar thing, and so the point of view that simplifies things is worthwhile. So if you don't have to be clear, if you don't have to worry about other planets, then you can assume that the Earth is in the middle of everything, and the sun rotates around. There is nothing wrong with that point of view, and so that's how you can predict, which practically speaking, you want to know where the sun is going to end up next time, or the moon for that matter, and then yeah. So once again, where do I put the center, the coordinate system? Where is the origin, the center of coordinate system? And the answer is at the Earth. Okay, and then the sun will be, so this is in the middle of the this is my Earth, and this is the sun. Okay, so that's mine. Pre-Copernicus solar system, but it works out perfectly well. That's why you would think that if they were so stupid before Copernicus, but somehow they were able to predict everything about the day and the length of the how long the day is and how the planets are moving. Well, they apparently were not so stupid, and the answer is because it doesn't matter as far as sun is concerned. that's quite predictable. If you, it's okay to think that the Earth is in the middle of the, and the sun is around. Okay, so anyway. Okay, so just a few words about bases. So it is about expressing vectors in terms of, in their terms. So the standard basis is literally the components that we have, or the that's what the picture shows, or the contributions of these two vectors to vector AB. So vector AB is vector A, the first component, B, the second one. It is literally how much of the first vector we have taken, A of them, and how much or how many vectors of the second vector we taken before we combine them together. So that's literally what it's supposed to mean. If we forget about components, it's literally the vector AB is decomposed into a linear combination of the vectors E1, E2, or IJs in this case. Okay, so you have 4 in this direction and 1 in that direction. That's what it is. So if we can do that with any other choice of vectors, why wouldn't? If we want to. So it's easy to replace. The easiest replacement would be this is the basis. Just as good. Okay, so that doesn't have to be necessarily pointing to the left. We could make we can do them this way. We can do them same directions but longer. Okay, so how about double? Okay, so this vector is 0, 2, 0, and this is 0, 2. All of these are legitimate bases. Okay, so once again, the only requirement is that you can express every vector as a linear combination of these. Okay, so then we can do it with in the n-dimensional case as well. Once again, these are the standard bases with one single one among all the zeros. And everything, once again, this idea that we had about dimension 2, it still applies to dimension n. This example is dimension 3. So once again, the components are nothing but contributions of each of the basis vectors to the sum. Okay, so like weights. Okay, and so once again, once it's understood, rather than writing it this way, so then we abandon this for the most part and concentrate on what this looks like. Then you realize that you don't really need to have the basis vectors to be standard, but you can replace it and have another one which you prefer. Okay, so so that's an example of how it works out here. As you can see, I replaced E with a negative E. I'm sorry, E2 replaced with negative E2. Okay, what effect does it have on the vector? So the original one is simply E1, E1 plus B E2. Okay, but I can also redo it this way. And so then my components that used to be AB in the standard basis, in the new basis, it will look like what? A negative B. A negative B is the components of the same vector with respect to the other basis. Yeah, so all of these are legitimate. So once again, the idea is how does it's not, when it does not work out is the case on the right, when the two vectors happen to be multiples of each other and therefore they cannot span. And that's literally the word that is being used to span a plane. Okay, two vectors that have an angle between them. If you put a fabric on them, like two planks, you'll have the whole plane. If they are like this, they are multiples of each other, then as you can see, the fabric is hanging down, and you're not getting the whole plane. So some vectors are missing. So that's what the basis in dimension 2. Basis in R2 is any such pair of vectors, V1, V2, that every vector can be represented as a linear combination of these vectors. That's all. Okay. And so now we realize that indeed on a typical example, we've had a bunch of them when these vectors could be the eigenvector. So linear operator can't but rather we can assign a new basis for the linear operator. So F, and especially good basis for F. Okay, meaning that in these directions, along these new axes, the operator doesn't stretching and nothing else. So once again, that's the two-dimensional case. Let's see, once again, the representation is unique. That once again, remember the investment advice. Remember that example makes also perfect sense. So express. So once again, there's good advice, and everything off of it is a bad advice. So you can choose then the good advice to be one of the basis vectors, and then the perpendicular to it would be how far you deviate from that advice. Okay, so we will look at that example. So once again, the convenience of choosing is what guides it in terms of which basis we pick. Okay, so naturally, in high dimensions, it's still the same story, except well, this is exactly the same. So once again, you have a particular combinations of stocks, bonds, whatever is suggested. What is it? It is a particular weights. So that's literally how frequently advice comes to you, investment advice. This percentage of stocks, growth stocks, this much, value stocks, 5%, corporate bonds, 3%. That's how the advice frequently comes. What does this limit us to? And the answer is they say hypothetically the semi-dimensional space. Actually, okay, the advice is the one-dimensional. It's a line. And so in the seven-dimensional spaces, there's a line, and that advisor suggests that you stick to that line. Naturally, it's never the case, especially every time the market moves, and therefore all of these are being repriced, and therefore you will, without doing anything, you will be off of that line. And so then you could express how far you are deviating from it by using that idea. So once again, n-dimensional basis. This is how we do algebra. Yeah, okay, so I think I'll stop here somewhere. Yeah, okay. So just the idea of basis is, I guess, it's the last. Let me mark it here. So this is the last topic. So the last topic for the final is this. So basic idea of what the alternative basis might be. Okay, so the link between, we haven't established the link between eigenvectors and these bases, but I hope you get the idea of why we want to have alternative bases for this number of reasons. Okay, so I'll have a few minutes left. So any questions about this? So okay, so let me say a couple of words, kind of about the whole thing. So so material is very tight, and so think a big picture. What's the big picture? If we try to think about the big picture of the whole thing, so it's only starting. We're only touching the basics of linear algebra. So what do we have take home, and meaning beyond the final exam is multidimensionality. I think the main idea is multidimensionality, which you can take home. So spaces of dimensions beyond 4. Okay, so that's the dimension of data is unlimited. So you have to be able to deal with it without visualizing it, which is impossible. So that's why you have to do algebra. But so we worked out that more or less. We took it pretty far. So Rn pretty much what are we talking about? This is Rn. That's really what the central concept. So a set made of strings of n numbers. And then to begin with, and then remember on top of that, the concepts that we added on top of that were distances. Okay, distances. So it's not just a bag of points. Okay, it has a structure. So you can do measurements. You can do angles. Once you also look at the vectors, you do algebra of vectors. And then, so it is where the data resides would be this. In the space, the data would reside. Even though you might measure the distances in a number of ways, nonetheless, probably a typical situation is that Rn, the usual Euclidean metric that you use, and therefore you have your vectors with the norm and the angles and the, that formula, the dot product, naturally, all of that is now in here. So once again, distances, the norm, the dot product, dot A dot B. Okay, so and then the last one which we didn't get, and that's the beyond, and it is you never look at these sets separately. You look at them. So what do these space, how they link to each other, and that's what linear operators are. Is how the these multidimensional spaces are linked to each other. Okay, so I'll stop here. If you have any questions, you can stick around and ask now. Meanwhile, I'll just so I'm still here.
Do we need